All right, so where we left off last time was we were going through this non-steady state problem where we're now considering the time component is an important part of the equation. So we make this assumption. We said it's lump capacitance. This body is lump capacitance. That just means that that the entire body we can model as having a single temperature, right? The temperature gradients from, say, the middle of the body to the edge of the body where it's losing heat or gaining heat are insignificant compared to the temperature difference to the surroundings. That lets us say it's like what we call lump capacitance, and we just now develop a single model or a model of a single point of temperature as a function of time only. Okay, so we went through it and started our analytical. We'll pick up, I guess, where we kind of left off, which was we got to this ODE here. We said dTd time is equal to some difference in the ambient temperature, which is changing as a function of time, and the temperature of the body, T, which is also changing as a function of time. Okay, so this is where we kind of left off, and then more specifically, we left off having solved for the homogeneous part of the equation and the particular part of the equation, and came up with basically a constants for the method of undetermined coefficients, right? Those coefficients multiplying our guess values. So let's just recap a little bit here. So we said the following. We said our temperature expression, right, which is TH plus TP, ended up being the homogeneous part was C1 times exponential of minus T over tau lumped, or tau LC. I'll just abbreviate it. Okay, that was the homogeneous part. And then the particular part, we did the method of undetermined coefficients. We guessed the right-hand side was some polynomial that had the same kind of form as our T infinity, right? We guessed it was some constant C, I guess C5 times T cubed and C4 times T squared. And right, we're just guessing the thing that's on the right-hand side and its derivatives. Okay, and then we had to go through and develop a set of equations to solve for that. And then, okay, if we went through, I didn't do it last time, if we went through, this is what we ended up with for those unknown constants. You just solve them in Maple, or it's pretty easy to solve it manually, actually. So we basically pinned down at this point what our final solution is. The particular part was, let's see, just C2 plus C3 T plus C4 T squared plus C5 T cubed, where those C's are given in the upper right there. Okay, so we got this far. Now the next step is we still have this, we have one unknown left, one unknown constant, C1, right? We don't know what that is. We haven't been able to solve for it yet. So we have to still enforce our boundary condition on this problem. Okay, now remember, this is a problem where we are just looking at the dependence of this body as a function of time. So the gradients in this problem, or the way that the problem is changing, is with time. So we need a boundary condition in time. And then in a boundary condition in time is called usually an initial condition. Okay, so for this problem, we were told the temperature at time equals 0, which is our initial condition, was some temperature T initial, which is a constant. This is some value that we would know or be given. Okay, so if we enforce this boundary condition, it looks something like this. We'd say T equals 0 is equal to C1 exponential of minus 0 over tau LC plus C2 plus C3 T, which is 0. So 0 plus C4 times 0 squared plus C5 times 0 cubed. And that has to equal T initial. And if we look at what this gives us, exponential of 0 is 1. Okay, and then these all go away. Right, and so we're just left with C1 plus C2 is equal to T initial. Okay, remember though, we know what C2 is. We already solved for it. It's that expression there up at the top. So I've just left it as what it is for convenience, but we really now just have solved for C1. Okay, we now have a full solution. Okay, so this gives us our full solution. We could go back now and actually plug this whole thing into ease and solve that problem. I think for the sake of time, I'm gonna see if unless I have it up already. No, I don't have it up. So for the sake of time, that example's there online. You could look at how we do it, but it's pretty straightforward. You just go plug it in, plug the equation in, and now you can evaluate for any given time that you have, you can evaluate the temperature. One thing to watch out for, which is like kind of obvious, but I just want to say it, is we're calling this here T, temperature, capital T. And in our solution, we're calling this T, lowercase t, time. If you try to do this in ease and copy it over pretty much directly and call both things T, it's not going to like that. So when you're doing things in ease, just make sure to call T like time, right? The word time. Just as a minor point. Okay. All right, so that gives us our analytical solution. Any questions on that part of it? I think that part is pretty straightforward, right? Okay, so let's do something a little slightly different for the boundary condition. So we have said now that our initial condition was t equals 0, but what happens if we have a situation where this little pulse of energy, this thing that we're trying to model as a function of time, let's say it's actually a repeating process. So you get this little burst that kind of comes and goes, but it repeats on a cyclical kind of timeline. So we might be interested in a situation where, not necessarily what's happening right at the left-hand side, right at the beginning, but we might be interested in what happens as it goes to, quote, steady state, right? It's still pulsing and changing with time, but we don't really care about that initial startup thing. We just care about what it's doing sort of as it's just operating long-term. So there's a way to deal with this, and it's kind of clever, but maybe not something you'd see right away. So this all just comes down to getting our general solution to fit the boundary conditions that we have, right? So what is a boundary condition that we could enforce to get what we would call the cyclic steady state? Okay, so what is our cyclical steady state boundary condition? Yes, exactly, right? So how would we enforce that? We would say the following. Where is this? So the boundary condition is T at T equals 0 has to equal T at T equals, what we would call this out here, let's say, T cycle. Right, T at T cycle. Okay, I mean, that makes sense. When we actually write it out, it would be, okay, well, what's evaluating our temperature at T equals 0? It would be C1 exponential of 0, right? So it just ends up being C1 plus C2. That's our temperature expression evaluated at time 0 has to equal our temperature expression evaluated at time T cycle, which is this, T cycle over tau LC, plus C2 plus C3 T cycle plus C4 T cycle squared plus C5 T cycle cubed. Okay, so this is a totally valid boundary condition. We're just trying to force our general solution to fit this particular situation. Yeah. So so if we are modeling it this way, it becomes the start of the cycle, right? So we kind of are shifting our coordinate system to match the problem that we want to model. And it just becomes convenient for us to specify T equals 0. I mean, you could pick that initial time to be anything you want, right? It's just going to make the algebra a little more messy. Okay, so this is actually something that I'm going to have you try out in the homework for next week. Okay, yeah.
Is the operator in front of C5
Sorry. No, should be a plus. Yeah.
Is C1 what we found from before, or is it a new undetermined?
No, it's the same one we found from before. Yeah. So we know, we know C1 already. We know all of these, in fact, right? C1, C2, C3, C4, and C5. Look back up here. We know C2 through C5 are due to the method of undetermined coefficients. Do you remember how we did that? We said, take all your t to the 0, t to the 1, t.
So from that, so we said C1 plus C2 is T initial
Uh-huh.
there, and then if that T initial the start of the period, the temperature at the start of the period.
Oh, I see what you're saying. I'm sorry. It's not the same one. Yeah, so sorry. So now we don't know. Okay, so we don't know C1. Sorry about that. Let's be clear. So we don't know C1. This is our boundary condition that lets us solve for C1, right? Sorry, that was backwards. Okay. Okay, so if we're all good with this, again, the example and the ease example for the sake of time, I'm going to skip that. We'll get into more of the code part of it in the second part here. But this example's here, and it shows how you might enforce that boundary condition and ease, and it's, I think, fairly straightforward. So.